Hello everyone, I am Avinanda Chakraborty. I am from Presidency University, Kolkata, India. And for the next few minutes, I'll be discussing my work on characterizing different quasar feedback modes through Sunyaev-Zel'dovich signal. Now, in 1940, George Gamow first predicted a relic blackbody radiation of about 10 Kelvin in the present universe. Later, in 1964, Penzias and Wilson discovered this cosmic microwave background or CMB radiation at a characteristic temperature of 3 Kelvin. Now, in 1989, after the launch of COVI satellite, it was found that the CMB spectrum perfectly matches with the blackbody radiation curve at a characteristic temperature of 2.73 Kelvin, which is a proof of isotropy and homogeneity in large scale. Now, this COVI also detected small scale temperature anisotropy in the CMB blackbody spectrum or in the order of 10 to the power minus 5. Now, the CMB temperature anisotropy comes from the density perturbation present in the universe. We can classify these anisotropies into two categories. One is the primary anisotropies, which is the early universe density perturbations. And apart from primary anisotropies, there are another anisotropy which is called the secondary anisotropies, which is the late universe anisotropies and which is caused due to the interaction of microwave photons and matter in the low redshift universe. In this picture, we can see the power spectrum of the cosmic microwave background radiation temperature anisotropy in terms of angular scale or multiple moment. Now, among all the secondary anisotropies, the most prominent one is the Sunyaev-Zeldovich signal or the SZ signal. So now this causes a spectral distortion in the CMB photon, which is caused due to the interaction of CMB photons with the hot electrons present in galaxy cluster. And this is a phenomenon of inverse Compton scattering. So now, but in our work, we are trying to detect the SZ signal from quasar feedbacks or the AGN feedback. Now, what is a quasar? Quasar is the most luminous active galactic nuclei or the AGN. Now, what is an active galactic nucleus? In most of the galaxies contain a supermassive black holes in their centers. And if it accretes masses from its surrounding, then it is called as active galactic nuclei. So in the right hand side, we can see a schematic diagram of an AGN or active galactic nuclei. And this is from Uri and Padavani 1995. So basically an active galactic nucleus is a compact region at the center of a galaxy that has a much higher than the normal luminosity, that is the stellar luminosity. And the accretion of interstellar gas onto supermassive black holes is the process responsible for powering active galactic nuclei. Now, what is a quasar feedback or an AGN feedback? So similar to feedback circuits, some part of accreted matters re-emitted from the AGN in terms of in the form of jets, relativistic jets, and the energetic outflow and gets recoupled with the intergalactic medium. This is called AGN feedback or quasar feedback. So we are trying to detect the SZ signal from quasar feedback. Now, this image is a observational evidence of the outflow of AGN or the feedback mode. So in this image, we can see this is a composite image of Chandra X-ray Observatory, Hubble Space Telescope, and Very Large Array. So Chandra is in X-ray, where Hubble is in visible, and radio, Very Large Array is in radio. So in this image, we can see in the galaxy cluster there is a diffuse X-ray emission from the hot gas, and we can see there is an AGN outflow in the red in terms of jet from the AGN. And from this image, we can see this AGN outflow is creating X-ray cavities in the hot gas, diffuse hot emission gas. So this is basically observational evidence that the outflows of AGN, and we are trying to detect the SZ signal from this outflow of AGNs. Now this SC signal is a very small signal, and it has been found that the Atacama Large Millimeter Array, or the ALMA, and the next generation very large array, which is the NGVLA, have the spatial resolution which can resolve this SC signal. Now, when we are trying to probe the SC signal from these two, using these two telescopes, but here I will discuss my work on the ALMA telescope only. So far, there is only one detection of Sunyaev-Zeldovich signal from quasar feedback. This was back in 2019 and done by Mark Lacey and his team. So after that, there is no such detection at all of the direct detection of Sunyaev-Zeldovich signal from quasar feedback. So in our work, we are trying to provide the tool or the template to the observers so that they can detect more Sunyaev-Zeldovich signal from quasar feedbacks, from more quasars. Okay, so in our work, we have used the SIMBA simulation, which is from the Dave et al. 2019, and which is basically a gizmo messless finite mass hydrodynamic cosmological simulation, which is a modified version of Gadget 3 simulation, and which has a box size of 100 megaparsec, and which also includes dark matter, gas dynamics, radiative cooling, star formation, black hole growth, and different feedback prescriptions. And from this simulation, we have used Redshift 1 and Redshift 0.016. And in the right-hand side, we can see a visualization of hydrodynamic simulation of cosmological structure formation using Gadget. Okay, so here comes our results. So these are all the AC theoretical AC maps at a frequency of 330 gigahertz, and in all the map we can see that it is at a redshift of around 1, and these are all the AC maps are all made around the black hole of 10 to the power 9.8 solar mass. And these black holes are from Dave et al. 2019 simulation, and in a region of 100 kiloparsec by 100 kiloparsec. These all maps are, and the number of pixels in all the images is 500 kiloparsec along the x-axis, and the 500 pixels in the y-axis too. So let us come to the feedback modes now. So here we can see different feedback modes available in the Dave et al. So in the upper panel, in the left hand side, we can see all feedback modes, which includes all the feedbacks in this map. And in the right hand side, this image includes no feedback at all. And in the lower two panel in the left hand side, we can see this image includes all the feedback except X-ray. And in this image includes, the right hand side includes all the feedback except the jet feedback. So from these 4 images, we have found that the AC signal is almost similar, and the highest at both at no feedback, for no feedback and no jet feedback mode, and that it gets reduced in case of no extra feedbacks, and is the lowest. The AC signal is the lowest for all feedback mode. This is for the redshift around 1. Now we have checked it for at a lower redshift, that is at a redshift lower, redshift at 0.016. And this is these AC maps are at a black hole, supermassive black hole of mass 10 to the power 10 solar mass, and all the other properties are similar as the previous one, like the frequencies at a 330 gigahertz, number of pixels is 500 by 500, and it is at a region of 100 kiloparsec by 100 kiloparsec. So from these 4 images also, what we have found that the AC signal from the central region is the highest for no jet feedback, then it gets reduced for no feedback, and then again gets reduced in case of no extra feedback, and the lowest AC signal from the central region we are getting from the all feedback modes. Okay, so next we check for the redshift evolution. That is, we check for all the feedback mode. We have compared the AC signal between two different redshifts, one at higher and one at lower. And in the upper two panel, for these all images, we have done what we have done. We have scaled the color bar just to compare these all the images. So in the upper panel, we can see for the all feedback mode, the lower redshift has the higher AC signal. But in case of no feedback mode, we have found that the higher redshift has little higher AC signal than the lower redshift. But in case of both no jet feedback and no X-ray feedback, we have found that for both the cases, lower redshifts have the higher signal than the higher redshifts. Okay, so next we make the mock observational ALMA AC map. So for that, what we have taken the redshift 1, and we have selected a region of 600 by 600 kiloparsec for the AC map, and here we have matched the ALMA spatial resolution, and according to that, the number of pixels were chosen. So why we have selected this? Because we are trying to match it with the teacup AGN, which is an observational to the observation. This is teacup AGN is at a redshift 1, is at a is an AGN at redshift 1, and which has the similar mass. So we are trying to match our AC map to that. So that's why we have specified these things. And to make the ALMA AC map, what we have done, we have run the ALMA pipeline to make the mock ALMA observational map using the CASA software. Okay, so in the upper panel, we can see this is for the all feedback mode, this is the theoretical AC map, and this is the mock ALMA observational AC map corresponding mock observational ALMA AC map. And these are also all the images, all the maps are also, in this case also, are made at a 330 gigahertz frequency. And in the lower panel, we can see it is the no feedback theoretical AC map, and it is the corresponding ALMA mock AC map for no feedback. And in this here we can see that in the left hand side, this is a theoretical AC map for no jet feedback mode for all the same specifications, and in the right hand side is the corresponding no jet feedback ALMA map, mock observational ALMA map for the similar black hole at a similar frequency as well. And in the lower panel also, we can see that it's a theoretical AC map for no X-ray feedback, and this is the corresponding ALMA mock observational AC map. So these are all preliminary results for our work. So what we have found so far from our work, we have found that the AC signal is the lowest for all feedback mode. And then it gets increased for the no X-ray feedback mode, and for no feedback and no jet feedback, we are getting similar AC signal, which is also the highest for in case of when the redshift is 1. But when the redshift is 0.016, we have found that the lowest signal is for all feedback mode, then it gets increased in terms of no X-ray, and then also again it gets increased in case of no feedback, and the highest AC signal we are getting for no jet feedback. Now when we compare the redshifts, where we have found that except for the no feedback mode, the other feedback, that's all feedback, no jet feedback, and no X-ray feedbacks, we are getting higher AC signal in case of lower redshift, that is redshift at 0.016. But for only in case of no feedback mode, we are getting slightly higher AC signal when the redshift is higher, that is redshift at 1. So we have also made mock observational ALMA map, and we are planning to, from that, we are planning to interpret observation from our those mock observational map, and also we are planning to compare our results with the TCAP AGN observation when it will ever happen in future. Thank you for listening. I am open to any kind of feedback, suggestions, and questions. Please get in touch with me in this email. Thank you.